Hello everyone, myself Rakhi, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Optical Communication, I am going to present before you Semiconductor Injection Laser. Semiconductor injection laser is basically a type of a laser about which we have studied in the previous lectures. So, in this particular lecture, I am going to cover before you introduction part of a semiconductor injection laser, then advantage of ILD over LED. ILD is our laser diode, then efficiency of our laser diode, then different modes of laser diode, and at last the single mode operation of a laser diode modes. So, this is the introduction part of the semiconductor injection laser. As we already know that the stimulated emission is the main reason behind the operation of a laser. So, in this case also the main reason and the main principle behind the amplification of light and the generation of the signal in the case of a semiconductor injection laser is our stimulated emission. So, stimulated emission by the recombination of injected carrier is encouraged in the semiconductor injection laser, which is also called as the injection laser diode or ILD, or simply the injection laser, by the provision of an optical cavity. So, in this particular laser diode, what we will have? We have a cavity. First thing, in the crystal structure, in order to provide the feedback of photons, why this cavity is inserted in the injection laser? For the feedback purpose. Feedback of what? That is the feedback of photons. This gives the injection lasers a major advantage over the semiconductor sources. So, what will be the benefit of this cavity for providing the advantage over the other one is that because this cavity provides the provision of feedback. So, what happened in the case of a stimulated emission, what we have already studied previously, that in the case of a stimulated emission, what we will do? We provide a stimulus. We provide the stimulus in the form of a signal, so that electrons, or we can say atoms at the higher level E2 get dropped into the lower level E1, and in this process it emits the photons. But in the case of what happened when we provide the external stimulus, this external stimulus excite the process of transfer of atoms from the higher energy level to the lower energy level, and in the process it emits the photon, and this stimulus is also emitted with the photon, and both this are in the phase. That is why we can say that the light emitted from the laser is the coherent one, and the laser is itself called as the coherent source of the light. And when this two, now we have, instead of a single photon which are used for the stimulus purpose, at first time we have a two types of two energy, so two photons. Now, this two photon, what it will do? It will excite two atoms. Previously, a single one is exciting the single atom, but Now we have a 2 photon and each one will excite 1 photon. So, now we are able to excite the 2 atom, and what will happen with the same process? 2 photons are emitted. So, now 2 here we have a 4 photon. So, and this process keeps on continuing and multiplication process continues. So, this is the major advantage in the case of a injection laser, and this is possible due to the presence of a feedback which is provided by this mirror. Which is attached at the end of the cavity, and it is called as the semiconductor because you can say GaAs, gallium arsenide, is our semiconductor, and you already know that this is our direct band gap semiconductor. Similarly, there is a p type, n type, and there exists a junction. So, this is a simple structure of a p-n junction, and that is why it is called as the semiconductor one, and injection because stimulus is provided and it works as a laser. It is used for the amplification purpose. So, this is called as the semiconductor injection laser, and the multiplication is the main phenomenon behind its advantage over other. It is able to emit light intensity, higher light intensity. This permits efficient coupling of the optical output power into the fiber, and it also permits the efficient coupling. What do you mean by the coupling? Everybody know about this, that coupling is a process by which we can provide the power from one medium to the other. So, what is the first medium here? The first medium here is our source, which is our semiconductor injection laser, and it has to be coupled with the fiber for the transmission. So, between the source and between the fiber, the coupling can be improved when use the semiconductor injection laser as the source. The spatial fold matching to the optical fiber which may be behind the laser, so is not possible with an incoherent emitter, and consequently the coupling coefficients are much reduced. When we use the incoherent one, the coupling efficiency can be reduced, but already we have seen that due to the presence of photons in same phase, we are able to achieve the coherent condition in the case of a laser. So, coupling efficiency are much improved in the case of a laser as compared to any other incoherent source, for example, LED. Now, advantage of ILD over LED. The high radiance due to amplifying effect of the stimulated emission, injection laser will generally supply milliwatts of optical output power. We already know that optical power which are generated are of very low intensity, but in the case of injection laser, since stimulated emission occurs, so the optical power get improved. Normally it is of microwatt when we use the LED, where the spontaneous emission is responsible for the emission of photons. About that we have already discussed in the previous lectures. Narrow line width on the order of 1 nanometer is or less, which is useful in minimizing the effect of material dispersion. As we have already know that in the case of a dispersion, what is going to be happen? Just have a recap of that, because we have already studied about this, that dispersion is a phenomenon by which broadening of signals take place. Broadening of signal takes place, and due to this broadening of signal, to adjacent signal interfere over each other, and so inter-symbol interference ISI will occur. So, these are the general description which occurs in the case of a dispersion, and we know that dispersion, the magnitude of dispersion which is occurring inside is directly proportional to the line width. So, if we want to reduce the dispersion, then we have to reduce the line width. So, here it is mentioned that narrow line width. In the case of a injection laser, we are able to achieve the narrow line width. And what is the advantage of this narrow line width? That we are able to reduce the dispersion mechanism. So, this is again a major advantage in the case of a injection laser over the LED. Now, modulation capability which are present extend up to into the gigahertz range and will undoubtedly improve upon. Modulation is basically a mechanism where we are able to change, in layman language we can say that modulation is a process by which we can either change some frequency or phase, so that our signal can be easily transmitted from the source to the destination. This is the general meaning of a modulation in the layman language. So, in this case, modulation capability that which generally exist in the case of a optical fiber is in the gigahertz range, but in the case of a injection laser we can improve this. So, this is again a major advantage, because the modulation capability of a system get improved due to the presence of injection laser. Relative temporal coherence, which is considered essential to allow heterodyne detection in light capacity system, but are present is primarily of use in the single mode system. So, in the case of coherence is a very useful phenomenon for the heterodyne detection. This is one of the detection mechanism. About that we will study when we study about the detection mechanism in the case of a optical fiber, and we will discuss about this in the coming slides and the coming lectures. But so, what is the important one? That is the coherence, and coherence is achieved in the case of a laser, and that is our semiconductor injection laser. That is why this is again advantage over LED, because in the case of a LED we are able to achieve the incoherent condition. Coherent condition can't be achieved in the case of a LED. So, in the case of a heterodyne detection system, that means at the receiver section, because this detection system is used in the case of a receiver one, we face a problem. So, it can be reduced, this can be reduced at the receiver section by the presence of a coherent system, and this can be achieved with the case of ILD, not with the LED. Good spatial coherence which allow the output to be focused by the lens into the spot which has a greater intensity than the dispersed unfocused emission. So, due to the presence of coherence, it has a greater intensity, focus can be increased, which can't be achieved by the dispersed unfocused emission. These are some of the advantage of ILD over the LED. Now, moving towards the efficiency. Efficiency is one of the major parameter for describing the output of the any system. So, here comes the efficiency of a semiconductor injection laser. The number of ways by which we operational efficiency of a semiconductor laser are defined. The first one, the useful definition of data differential external quantum efficiency ND. So, again we have already discussed about this in previous lecture, but for the recap one, external quantum efficiency. So, external quantum efficiency is used for the stimulated emission because in the for existence of stimulated emission we required a external stimuli, then only stimulated emission can be possible, and this is the main reason for the power output of the laser. So, here comes the external quantum efficiency, but in the case of a laser both external and internal quantum efficiency comes, because in laser both spontaneous and stimulated emission are responsible for the emission of photons at the output. So, first we are going to have a external quantum efficiency which is due to the stimulated emission, and then we will discuss also about the internal quantum efficiency in which occurs due to the occurrence of spontaneous emission, because in spontaneous emission no external stimulus or power is required, it occurs randomly. So, external quantum efficiency is the ratio of the increase in the photon output rate for a given increase in the number of injected electron. Photon output rate, increase in the photon output rate due to the increase in the number of injected electron, because what is obtained at the output of the laser? We obtain photon, and what is given inside? That is the electron. So, ratio between the photon upon electron. If P is the optical power emitted from the device, I is the current, E is the charge on an electron, and HF is the photon energy, then the external quantum efficiency is given by this formula. E bar, and then it can be further reduced with the Eg, where Eg is the band gap energy which exists between the higher energy level and the lower energy level. And D gives the measure of the rate of change of optical output power with current, and hence defines the slope of the output characteristic in the lasing region for a particular device. And D is of course the ratio, that is why it can be defined in the terms of slope of the power and current, because slope is always the ratio between the anything in the y axis to the anything in the x axis. So, ND is sometimes referred to as the slope quantum efficiency. For a continuous wave semiconductor laser, it usually has a value ranging from 40 to 60%, a very good efficiency. Alternatively, the internal quantum efficiency, which occurs due to the spontaneous emission, is given by the number of photons produced in the laser cavity upon the number of injected electron, may be quite high with values usually in the range of 50 to 100%. It is related to the differential external quantum efficiency by the expression this one, where this is the external quantum efficiency, this is the internal quantum efficiency. Alpha bar is the loss coefficient of the laser cavity, L is the length of the laser cavity, R1 and R2 are basically the mirror reflectivities, because we can see that here exists two mirror and here the length of the cavity, that is L. Another parameter for defining the efficiency of a injection laser, total efficiency NT, which is given by total number of output photons upon total number of injected electrons. which is given by this, and don't be confused with the external and the total, because external is the differential one and this is the complete PE. As the power emitted PE changes linearly when the injected current I is greater than the threshold. We already know that in the case of a laser, a threshold value has to be achieved because external stimuli is applied and external stimuli provides that threshold current. So, it has to be achieved so that the process of lasing can start. So, how it is related? Total efficiency related with the external efficiency by this formula, and for in the case of a injection laser, we can make total equal to the external one by putting I is equal to n. This can happen, whereas for lower current this can be by this one. So, at last the external power efficiency of the device NEP can be obtained by this formula, where P is equal to I into V and into 100%, and we can write this in this form also. NEP is equal to NT Eg upon V. This can be achieved by using this formula, because we can see that P by I is our, if we want the so P by I is equal to NT into Eg. So, we can substitute this in this equation. P by is equal to NT into Eg and V same as the denominator. Now, the question, one numerical, the total efficiency of an injection laser with a gallium arsenide active region is 80%. So, what is given? Efficiency, total efficiency, is equal to 18%, which can be written as 18 upon 100. The voltage applied to the device is 2.5, V is equal to 2.5 volt. Band gap energy, that is Eg, is equal to 1.43 volt. Calculate the external power efficiency of the device. That what you have to calculate? We have to calculate this one, external power efficiency, external power efficiency. Now, which formula can be used? This one can be used for calculating. So, let us do this. So, NEP is equal to NT, already seen by you, Eg upon V into 100%, Eg upon V. So, what is NT here? 18 by 100, Eg 1.43 and V is your 2.5 volt, and we want the result in the percentage. So, 100%, and when we solve it, we get it as approximately 10%, and all of you are requested to please solve it, because this is just a formula based question, and see whether you are achieving this answer or not. Now, the laser modes. As we know that in all the cases, in all the devices, we have a different modes existence. So, in the same as in laser also, there exists a different type of modes. The typical output spectrum for the broad area injection laser is shown here. This is the spectrum of a broad area injection laser. It does not consist of a single wavelength, because we know that modes is directly proportional to frequency or wavelength. It is related to wavelength and frequency. So, if there exists a different modes, that means it does not consist of a single wavelength output. It contains a multiple wavelength output, but a series of wavelength peaks corresponding to different longitudinal, that is in plane of the junction, along the optical cavity modes within the structure. This spectrum clearly indicates that in output we achieve a different wavelength of a signal, not a single one. The spacing of this mode is dependent on the optical cavity length, that is our L, and we have already seen the structure. There exists a mirror and there is the complete length of a cavity. As each one of the correspond to the integral number of length, the spacing between the modes, that is between this spacing between the modes we are talking about. They are generally separated by a few tenths of nanometer. These are the normal value, and the laser is said to be a multi-mode device because there exists a number of mode and number of wavelength. Now, the single mode. For single mode operation, the optical output from a laser must contain only a single longitudinal and a single transverse mode. So, what we are saying in this case, that we have seen that in laser mode there exist multiple modes, and that means multiple wavelength. But for single mode operation, we required a single either longitudinal or a transverse mode. Hence, the spectral width of the emission from a single mode device is far smaller than the broadened transition line width, because in the case of a single mode device, the spectral width, we are talking about the spectral width, which is normally denoted by sigma lambda, is much smaller than the broadened transition line width, is much smaller than which exists for the multi-mode, and already known to you and already discussed in this class also and in the previous lectures also, that this line width is directly proportional to the dispersion. And if we want to reduce the dispersion, we have to reduce this spectrum. So, this single mode achievement is a very important thing in the case of a laser diode operation. Single transverse mode operation may be obtained by, how it can be obtained? By reducing the aperture of the resonant cavity such that only a single mode is supported. To obtain a single mode operation, it is then necessary to eliminate all but one of the longitudinal mode. One method of achieving single longitudinal mode of operation is to reduce the length of L of the cavity. L को reduce करना is one of the method until the frequency separation of the adjacent mode. Frequency separation between the adjacent mode, which is given by this equation, is larger than the transition line width or gain curve. Then only a single mode which falls within the transition line width can oscillate within the laser cavity. So, we have to follow this two condition for the laser mode operation. And when the laser mode operation can be achieved, we are able to get a single peak of a wavelength. However, it is clear that a rigid control of the cavity parameters. So, only by controlling over the cavity parameters, we are able to do this. So, in this particular lecture, we have studied about the semiconductor injection laser, its various type, and why the single mode is necessary for us. So, thank you for attending today's lecture.